Okay, welcome to this problem. In this problem, I'm going to be talking about an object that's dropped from rest from a height of 10 meters, and I'm going to find the speed right before it hits the ground. So I'm going to use a basic application of energy to solve this, okay? So here's your object. It's released from rest, and it's going to start falling, and eventually it's going to hit the ground. But I'm going to find the speed right before it hits the ground. So I can label these different points in time. So this is going to be point A, this is going to be point B, this is going to be point C. Now the mechanical energy of the system is going to be conserved. So the energy of A is going to equal the energy of B. It's going to equal the energy of C. The total mechanical energy is going to be conserved. So if I went over here and I started to write this equation out of conservation, I would end up with saying that the energy of A equals the energy of B equals the energy of C. Now I'm not going to put an arrow above it because this is not a vector. This is energy. The energy at A equals the potential energy of A plus the kinetic energy of A. And energy at C is going to equal the potential energy of C plus the kinetic energy of C. So what I can end up doing is I can compare my initial and my final state. Okay, so I'm just going to go ahead and I'm going to set the energy of A equal to the energy of C. So I'm going to say the energy of A equals the energy of C. And I know the energy of A is going to be the potential of A plus the kinetic of A equals the potential of C plus the kinetic of C. Just comparing these two states, they're equal. I'm assuming there's no friction. Okay, so when I'm released from rest, this is from rest here. Okay, so this is from rest. So right here, this is rest. I'm going to assume that I have a maximum potential energy and a kinetic energy that's zero. It's from rest. When it's falling here and it's at the ground, I'm going to assume that my potential energy is at zero and my kinetic is going to be maximum. So I'm going to end up saying that the potential energy of A, all of that potential energy is going to be converted to kinetic energy at C. So the potential energy of A is simply going to be mgh of A equals 1/2 mv squared of C. Okay? So that's what I'm going to be using here to find the final speed at the ground. Now I'm going to go down here a little bit further. I'm going to keep writing down here. So I'm going to say mgh of A equals 1/2 mv squared of C. Once again, I'm just going to rewrite this down here. I'm going to notice something here that is very convenient when you're dealing with energy. First of all, it doesn't matter what happens in between. It's just comparing the before and the after. And the masses here are going to cancel when we're dealing with this. So the speed of C, at this case, is going to be the square root of 2gh. Okay, so what did I do? Well, I multiplied the 2 over. Okay, multiplied the 2 over, and then it was going to be v squared equals 2gh, so v is the square root of 2gh. That's the speed of an object when it's released from rest right before it hits the ground. So the speed right before it hits the ground is the square root of 2, and I'm going to go ahead and use 10 for g, and 10 was my height. Okay, so my speed right before it hits the ground is going to be the square root of 200, right? Or I can factor that out. I have a 2 and 100, right? So I can basically make that the final speed is going to be 10 root 2 meters per second. And that's the speed right before it hits the ground. Okay, so this is a basic application of energy, and we're just finding the speed right before it hits the ground, and we did not need to know mass to solve that. Alright, that's all I got for this video. Thanks for watching, and I'll talk to you soon.